turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith, and today we're going behind the scenes at the National Physical Laboratory, NPL, as it celebrates 125 years at the forefront of science. The National Physical Laboratory, or NPL, was founded in Teddington in southwest London in 1900, which means that this year marks its 125th birthday. It's a huge milestone for NPL, which is the UK's national measurement standards laboratory and also the guardian of the physical standards that dictate modern British industry. The world's first atomic clock was built there in 1955, and today its pioneering work in quantum technology as well as artificial intelligence are helping to drive the UK's scientific renaissance. But why was it set up in the first place? Here's JT Jansen, who's Chief Scientist and International Director at NPL.
If you want to trade with a foreign country and you want to sell them something, they need to know what they're buying. And you both need to agree on what it is you're selling. For instance, if you sell a kilo of potatoes to somebody, that other person wants to know that you've really sold them a kilo of potatoes. And that means you both have to agree on what a kilo is. And that sort of perpetuates through all measurements which we do. And we do loads of measurements. You do measurements of weight, length, temperature, electrical properties, current, voltage, and all these kind of measurements of really important units need to be agreed internationally. And that means that the UK has a national measurement laboratory, NPL, and also all the other countries around the world have got national measurement laboratories. And it wouldn't surprise you that Germany was one of the first ones to have a national measurement laboratory. Then came the UK with NPL, and very soon afterwards there was the National Institute of Standards and Technology set up in the US. And basically most measurement laboratories were set up as support for international trade and economy.
It's interesting though, isn't it? Because although we might have had those standards emerging, there were still multiple ways of measuring the same thing. Let's take the difference between metric and imperial, for example, and the Americans still use imperial. In fact, we've ended up with rocket disasters because people disagreed over the size of a bolt that was imperial in one country and metric in another. So in some respects, it was founded on a sound principle, but it still hasn't solved all the problems, has it?
95% of the world uses the international system of units, the metric system. And of course, there are still local standards, like we still talk about a pint of beer, but we know that a pint of beer is exactly 500 and something milliliters. All these other units are still defined in terms of the metric system. And the errors occur when people use the wrong conversion factors between the sort of traditional units which you used to use and the sort of internationally agreed metric units.
Was the whole idea about standardising in this way well received across the world, though? So when NPL got set up and said, look, we need to agree on what a kilo is, we need to agree on what a second is, was everyone on the same page?
The history of standards and measurements is very long. It started with the building of the pyramids by the Egyptians, and there were many local standards. There were many rows about standards, and also people used standards to establish their empire and thereby control the way they taxed and traded. And when the current system was set up with the Meter Convention 150 years ago, the UK was one of the countries which didn't sign the Meter Convention because it thought that it would have an adverse effect on British trade and economy. Very soon, of course, they realized that if the others are grouping together around one metric system, then we really ought to be joining it, because otherwise you'll start to lose out because people will not want to trade with you.
And is that how the meter came to being, and metrication in the UK came into being then?
The UK has actually been using metric units for a very long time, even though in popular parlance we still use, of course, all the imperial units.
Yeah, one wonders how stones and pounds and pints have hung on for so long, nevertheless. It does seem surprising, doesn't it? What were the main priorities for NPL when it got started, apart from getting the measures right? What were the main scientific priorities and goals?
The first priority was to be competitive with countries like Germany and the US and protect UK trade and manufacturing through joining that system. But very soon afterwards, of course, as a country, you want to have your own realizations of the unit. So you want to have your own copy of the kilogram, you want to have your own meter, you want to have your own temperature scale. Of course, that gives you a level of autonomy and priority. So that was really, in the very first instance, to establish those primary realizations.
When they actually first began to make those kilograms and then distribute them around the world, so you've got a counterpart in every country which has got its own kilo, did they literally make them all together, weigh them against a standard, and then give everyone one to say that's your kilo so that everyone knew they were on the same kilogram scale?
The first batch of kilograms was made here in the UK by Johnson Matthey, and they made a whole series of kilograms in one go. And they chose one which became Le Grand K, which was basically the kilogram which was kept in a vault in Paris, and all the other ones were direct copies of this 1 kilogram. Over the period of the last 150 years, the kilograms which were distributed around the world came back to Paris and were compared with this original kilogram. And of course, over time, they saw that the spread of the kilograms becomes bigger and bigger.
That's quite an auspicious track record, isn't it? That was JT Jansen, who's Chief Scientist and International Director at NPL in Teddington. The National Physical Laboratory doesn't just deal with standards in weight measurements. It's also been at the forefront of precise timekeeping too, including pioneering the development of atomic and now optical clocks that are so accurate that they lose less than a second over the entire age of the universe. It is hugely impressive. And here's Rachel Godin, who works on NPL's next generation of optical clocks.
NPL has a very proud history of timekeeping. This began with the development of the world's first atomic clock in 1955 by Louis Essen and his team. What they were able to achieve was a clock which was more accurate than any clock of its time. This was a real transformation in the level of accuracy of timekeeping.
How did people actually decide what a second was before we had an atomic clock to keep us on track?
For a long time, up until in fact 1960, 1 second was defined so that the length of a day would be 24 hours of 60 minutes and 60 seconds. So the idea was to take the mean kind of rotation time of the Earth about its own axis and then subdivide that down into the hours, minutes and seconds. And that would then give us a fixed interval for 1 second.
Although, as we've seen this year, the Earth doesn't always spin at the same speed. So we're potentially therefore introducing some inaccuracy if we go by that physical way of doing it. And I guess that must have been one of the motivations to have a system like an atomic clock that's divorced from that.
That's exactly right. And somewhere around the sort of 1930s, 1940s, people actually started to suspect that the Earth didn't rotate at a nice even speed, and that maybe it was a little bit wobbly in its rotational speed. And it wasn't until having very accurate atomic clocks that people could definitively measure that and see that, yes, indeed, the Earth is a little bit wobbly, and it wasn't therefore a very good way to define a second. So between 1960 and 1967, it was recognized that, oh dear, we've been using the definition of the second based on the Earth's rotation that's a bit wobbly. We should redefine the second to be based on something that's a much more fixed period of time. And the choice was made to define the second to be a fraction of the Earth's orbit around the Sun in the year 1900. So now you have the definition based on a fixed length of time, but this is a really difficult definition to use. This really wasn't very workable. And so in 1967, the second was redefined again to be based on an atomic clock. This is now still the definition that we use today, to be basing 1 second on a cesium atom. And it's got us away from the difficulties of needing astronomical observations to tell the time.
How does that actually work, using an atom, in this case cesium, to tell time?
Atoms have the property that they have resonant frequencies. You can excite a cesium atom if you shine microwaves at it, And if you tune the microwaves into the frequency that matches the atomic resonance frequency, this now gives you a wave of microwaves that's oscillating up and down. And so you can use that wave, you can think of the ups and the downs of the waves as the sort of tick-tock of the clock. So you now have a microwave that's been tuned to match the cesium's specific frequency. And the beauty of that is that it means that if you have a cesium clock in one place or a cesium clock somewhere else, anybody who tunes their microwaves to match the cesium's resonance will be tuning their microwaves to the same frequency.
It's a bit like when you push someone on a swing, isn't it? When you give them a push at the right time, the swing swings higher and higher until they reach peak swing. But how do you know what the cesium atom is doing? How is that registered so that you know you have tuned your microwave pulses into the resonant frequency of the cesium to get that timing perfect?
Yes, so we need to be able to see when the cesium atom has been excited. And so that comes down to being able to determine what internal energy level the atom is sitting in. And so by trying to excite internal energy levels with laser light, you can determine whether it was in the ground state or the excited state. So the idea is that you prepare the atom in the ground state, you send in some microwaves, you see if it's been excited. This is how you get the information as to whether your frequency was hitting the resonant frequency or not.
Are microwaves and therefore atomic clocks based on cesium sufficiently accurate, though? Because there's going to be an inherent frequency limitation with a microwave, and there are forms of radiation which are far, far higher frequencies and therefore presumably have much better resolution of timekeeping. So why don't we go better?
Initially, this first atomic clock that was developed at NPL in 1955 was based on cesium, and so we've stuck with that for a while. It actually turned out to be a very good choice. The cesium clocks that we have nowadays, you can use them to measure 1 second to 16 decimal places. So these are the clocks that underpin national and international timescales. So they're reassuringly accurate. But as you've raised higher frequencies, enable you to reach better accuracies. And so this is a general sort of principle. If your clock ticks faster, it's easier to subdivide an interval of time into smaller and smaller time intervals. So if we could have an atomic clock that's based not on a microwave frequency that's ticking at about 9 billion ticks per second, but if we could have, for example, an optical frequency, so using a wave of laser light, this can tick about 100,000 times faster. And this is going to then unlock a new level of performance.
And those will then tick at those correspondingly higher frequencies, so you would get that extra precision, that higher resolution of timekeeping. That's
right. And these so-called now optical atomic clocks are able to measure 1 second to 18 decimal places. So 100 times better performance than the cesium clocks that are currently used for the definition of the second.
Now, we started talking about how we first defined the second. Will we see the second change again? Because you've mentioned that we used to do it by how fast the Earth was spinning, then we were doing it by how fast the Earth's going around the sun, then we're doing it by the atomic clock. Is there going to be a fourth definition of the second, or are we done?
No, we are very much anticipating right now a new definition of the second. These optical atomic clocks having an accuracy that's 100 times better than the cesium clocks. This is causing us to say, hang on a minute, we've got clocks that are already 100 times more accurate than the cesium clocks. So, we should redefine again. The international metrology community is currently targeting 2030 as the date for a new definition of the second based on an optical atomic clock. And that would then unlock 100 times improvement in the accuracy with which people can tell the time.
Whoever it was who said time doesn't stand still, they were absolutely right, weren't they?
Certainly, yes. And there are all sorts of interesting problems that you encounter when you start to get to this 10 to the minus 18 level of accuracy. And I think a very kind of interesting problem is that of general relativity. So general relativity tells us that time runs at different rates in different gravity potentials. So that means at different heights above the Earth's surface, time would actually run at a different rate. But the scale of the effect is that for every meter change in height, time itself, and therefore your clocks, would tick differently by a part in 10 to the 16. So if we now have clocks that are able to be accurate at the part in 10 to the 18 level, it means that they can resolve a change in height of just 1 centimeter. So we've really got to be not only making our clocks accurate, but also being very aware of the environment that they are. If we're trying to build an international timescale where we're comparing lots of clocks together, we need to have knowledge of their height differences at the centimeter level. It's a huge challenge.
Because, of course, my feet are aging at a different rate than my head, aren't they, for the very reason you've just outlined?
That's right. And the scale of that effect is it's about a couple of nanoseconds per year that your head would be aging faster than your feet. So yeah, you can decide if that's a worrying amount of difference or not. It's certainly a very odd concept.
It is indeed, but that was so interesting, I hardly noticed any time passing. Did you? That was Rachel Godin.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
And this is the Naked Scientist podcast with me, Chris Smith. And today we are going behind the scenes at NPL, the National Physical Laboratory, which is celebrating its 125th birthday. In a minute, we'll find out about NPL's role in harnessing and safeguarding emerging AI technologies. But first, we're going to delve into the quantum world, a field that seeks to use the weird rules of quantum physics to create powerful new computers, sensors, and communications systems. The National Physical Laboratory has played a major role in the development of quantum science throughout its history. Here's Chris Coggs.
100 years ago, a bunch of really great scientists and really world-leading really laid the foundations for quantum mechanics and quantum technology as we know it today. And then ever since that time, you've had a wealth of scientists throughout the decades really trying to delve in on those theories and try and understand kind of the fundamental building blocks of life. So all the changes that happen at the atomic level, how interaction from atoms to atoms work, and ultimately how life functions.
A lot of those scientists you cite, they actually famously, or at least two of them, have said if you weren't baffled by quantum mechanics, then you just didn't understand it. I think Richard Feynman went a bit further and said if you think you understand quantum mechanics, you didn't understand it. So I mean, it's clearly a very hard to access thing. Just in a nutshell, when we're talking about the quantum world, what do we actually mean?
At the very fundamental point, you essentially have how the energy of each of our electrons and protons and neutrons, how those energies all interact and relate to each other. And so what you can do then is you can build up technologies based upon these fundamental building blocks, and you can do some really great science that you then do with interacting them or entangling them, as we call it. And that's where really the fundamental parts of quantum computing can come from, is using building blocks of physics to do computation.
Why is a quantum computer regarded as the holy grail? Why is it potentially so much more powerful than the best computers, the best supercomputers that we can build today?
So you can kind of think about quantum computers that they work very differently to today's supercomputers. So some of the ways that classical supercomputers work. The anticipation and the expectation is that quantum computers will eventually be able to solve problems much faster than today's supercomputers, but also problems that are so hard that even running them on the most powerful supercomputers that we can think of today or hope to think of in the future, they just wouldn't be possible. And so you start to bring in problems, really fundamental chemistry problems or material science problems that would be out of reach for most computation. You also have aspects of slightly more real-world applications in finance or transport or medicine, where quantum computers, if they actually arrive and do what they're expected to do, should be able to unlock options for moving items around the globe or for making sure that information is secured to transfer between different people and organizations.
Where are we along the path towards realising this, though? That's the aspiration. Sounds fantastic, but how far are we away? Is it like nuclear fusion where people say it's 10 years away and it always will be? Or is this about to be realised, or has it already been realised?
So I've been working in the field not too long, really, in comparison to many of our other colleagues. But actually in that time, I've seen a huge acceleration of what people were claiming quantum computing, quantum sensors, and quantum networks and what they can do. So I would say that we are really rapidly accelerating. And because more focus is now put on quantum computing, there's a real push from governments, from industry, from academia to really kind of drive this innovation. So progress that would have been made in the last 100 years is actually really starting to condense a lot more down. And you see step changes occurring a lot quicker than we have in the past.
I thought you were going to say there's going to be a quantum leap. I thought you were going to go down that path for a minute. But what's NPL's role going to be in this then? Because this is very much the preserve of industry and technology to invest in order to make the breakthroughs that are going to make this realisable. Where does NPL come in?
NPL were working on quantum long before it ever became quantum. If you think about some of the clockwork that we do, we built the first atomic clock in the world, and that's essentially on fundamental quantum principles. And then from there, we've just been building upon that. So we've been building technologies, we've been supporting industry and building their technologies as well. And we work throughout. So we work with academia, universities, we work with industry, we work with government to help identify problems, issues, and challenges that they might face when dealing with quantum technologies and help them to overcome those barriers. So one of the main problems we have right now is how to scale some of these technologies. And when we mean scale, we don't just mean, make them bigger. What we actually mean is making them have the same properties and performance when you start to increase things like the number of qubits. Or you might look at how you can make countrywide quantum networks, taking it out of the lab from a lab bench and really putting it into a critical national infrastructure, like a communications network.
Is that what you're working on right now?
Yeah, so we actually work with companies to help them develop their qubits. We help them to develop their sensors that will essentially be used to map things like gravity or brain imaging and brain scanning. We can work with companies to help develop their really secure communication technologies. And all of these wrapped up is really where kind of NPL has its bread and butter in measurements and standards.
Chris Cox, who works on quantum technology at NPL. Well, now we're going to venture into the realm of artificial intelligence, an emerging technology that's made its presence felt in what feels like record time in almost every aspect of our lives. Sandeep Bhandari is NPL's head of digital innovation, and AI is very much his domain.
So measurements are often seen as this invisible utility that without which things actually wouldn't move, anything from basic blue skies research and development done in laboratories all the way through to large commercial entrepreneurship and those kind of activities. All of those things rely upon the ability to go back to a set of measurements to have that traceability and that immutable proof. Now, it's one thing if NPL does that just for the UK, but we need to trade, we need to travel, we need to innovate, invest, make, manufacture all across borders. So how do we then make sure that this system of units works across these borders? And that kind of then brings us towards AI. So the underpinning quality infrastructure, the ability to measure and have confidence in the data going into these systems, and then the learning outputs coming from the AI systems doesn't yet exist. So if we want to leverage all of the benefits and opportunities that AI could bring us in terms of saving lives, being more efficient, helping with the climate change challenges, we really do need to have a way of being able to have confidence in what the AI is doing.
So is it that you're trying to anticipate, well, what will we need to measure? What will we need to have policies around? What will we need to have a sort of framework in order to do? And you anticipate where the technology and those sorts of things are going to need to intersect. Is that your role?
I would say that's part of our role. One of the key things that NPL is tasked with, apart from being one of the core components of the UK's national measurement system, is that we are specifically asked to look at supporting industrial innovation and helping accelerate the SMEs, the small and medium-sized enterprises within the UK, as well as the large multinationals. So helping to develop industries of the future, but giving them the confidence through measurement that they can innovate, they can develop new technologies, they can do the research. So part of our role is essentially to help others accelerate and enable others to deliver impact, be it through business or by saving lives or by developing the right policies that enable these technologies to flourish in a positive way.
Now, when it comes to things like the kilogram, you've got one of those. When it comes to the second, as we heard from Rachel earlier, well, you've got an atomic clock or two and you can deal with that. When it comes to AI, what's going to be your standard, or what could you show us to say, well, there's the AI equivalent of the mass that is the kilogram that you set the record by?
So that's a great question, and that's exactly what we're starting to work on right now, is to develop the approaches. So some of our colleagues within the data science and AI department have already developed the first version of the trustworthy and safe AI lifecycle, which enables us to go through methodically how we would approach these metrics. We have some measurement capabilities already for AI. So most recent example was helping some of the wearable device companies understand how much confidence they could have in using your smartwatch to measure atrial fibrillation, for example. So for that kind of work, not only did we get the wearable manufacturers in the room, we got clinicians, we also got people from the medical regulations authorities, as well as then potential patients, and really getting a holistic view on the types of questions and the kinds of context we need to be thinking about to explain how much confidence you can have in that device. So I would say we're on the journey. We've definitely started to do a lot of work, but there's a lot more to be done, and it can't happen in isolation through NPL.
A lot of people, though, have said there's disquiet around the fact that this is moving very, very quickly, and the technology is way outpacing regulation or our ability to make guesses about where the risks and threats may lie. Where do you sit on that argument? Do you think that it is going too fast and we need a bit of breathing space, or do you think actually it'll all come good in the end?
So I definitely agree with it moving fast. Often when I stand up and present, my last line at the presentation is, by the time we finish this meeting here today, there'll be 2 more algorithms or 2 more models that I need to go off and now worry about or think about. I don't think we need to take a wholesale pause. Anybody, even with the best of intentions, that did try to cause that pause wouldn't be able to actually stop what goes on out in the outside world, be it in the UK or further afield. So what I would think is our take on this is actually, let's make sure we've got the fundamentals and the foundations correct. So what are those sector or application agnostic things that we can measure and building blocks that we can then use to apply to other ways of evaluating AI? We're very much thinking about what we need to do about the large language model side of things, because that is evolving very rapidly. But I think it really, for us, comes down to breaking it down into understandable bite-sized chunks and then starting to stitch those blocks together to then get even more capability to understand and evaluate AI with confidence.
If we take a climate change analogy, though, we're now grappling in the here and now with our enhanced understanding of the impact we have on the planet, measured in the multiple billions to potentially 1 trillion tonnes of carbon dioxide up there. Is there not a risk that if we just allow these runaway trains of large language models and so on to do their thing, that by the time you catch up and work out how to gauge the risk and mitigate it, the knowledge space will have been heavily polluted by the deleterious aspects of some of these models, the things they confabulate and so on, and we may then have quite a clean-up on our hands?
I think there's a big skills and an education piece that needs to happen. These very large language models that we're now seeing advertised on television and are constantly on our digital feeds are very much generalist type of applications. What we're seeing more and more of is to really leverage the power of these tools and technologies, and they are very powerful and could be very useful. In fact, they already are very useful. But the way to really harness that is make them a bit more focused. At the minute, we call them large language models. The approach we're looking at is, what do small, narrow language models look like, for example? So this could be anything similar to some of the systems we've developed at NPL for our own uses, where the only data that's used to train these models is data that we have put in there and data that we understand, or is only pointed towards external sources of trusted data, and then asked to only perform very specific tasks within specific contexts and applications. So essentially cutting out some of that noise and therefore some of the risk. It allows us to then get highly accurate answers to questions that you could ask of a normal large language model, but would not get the same quality of response from.
But nevertheless, there's still been some pollution in the meantime, which may then contaminate even very focused models down the track.
Absolutely agree with that. And that's part of the other line that I often show. So whilst I'm saying that line about the fact that I now have to deal with more AI models and tools after having finished this presentation, the picture on the slide is actually a big picture of a data lifecycle. So the point there is there's a whole piece of work that sits alongside our AI science research in terms of data quality frameworks, understanding the confidence you can have in the data that you're actually putting into a system or that's already in a system. And so again, it comes back down to the question of how critical is this application? Is it going to ruin my business? Is it going to harm someone? Is it going to cause unnecessary environmental impact? So understanding the quality of your data is quite a key element before we can really have confidence in using these language models for critical applications.
Sandeep Bhandari, who's Head of Digital Innovation at the National Physical Laboratory. We began this week by looking back at the last 125 years of NPL's history. But what does the future look like? Chief Scientist and International Director, J.T. Jansen again.
More accurate measurements, always the history of science, have led to new discoveries and often open up a new world of seeing things. So often when we make new precise measurements, people often ask what's the use of that? And often the real opportunities and applications come many years later. And that's really the strength of measurement science. It opens a new window into the future if you can measure things a lot more accurate.
J.T. Jansen, and happy birthday indeed to everyone at NPL. Here is to another 125 years. That's it for this episode. Join us on Friday, though, for the latest science news. We're going to be hearing from Baroness Cathy Ashton about the importance of space innovation to the UK's economic recovery, and we also have a story which is some good news on the antibiotic front. Meanwhile, if you enjoy what we do for you every week and you'd like to help us out with our running costs, do please drop into nakedscientist.com/donate. We really appreciate your contributions to keeping the show on the road. And please do also leave us a review wherever you get your podcasts, or if you prefer, you can follow us on LinkedIn, on Instagram, and on X. The Naked Scientist is supported by Rolls-Royce. I'm Chris Smith, and from everyone here at the Naked Scientist team, thanks for listening, and until next time, goodbye.